Let us start today's session. So I welcome you to this problem solving and live interaction session for the subject engineering mechanics. So today we will be looking at problems from week 12, which has to do with kinetics, 2D kinetics of rigid bodies. So let us look at the first question. So it says, if a force is applied to a pinned rigid bar initially at rest, and if this generates no reaction at the pin joint at the instant of that application, then the location of the point of application of the force is which of the following? So basically, we know even towards the next questions, we have one example for that. What we mean is that basically we have a bar which is pinned like that, and then we are applying a force at some point. Let us say this is F. Let the force be F, and then we are applying it at some point, some special point P, such that if we were to draw, now we have this. If I have to draw the free body diagram for this, so I need to eliminate the pin there, and we know that pin has two components of forces because it is resisting translation. So let this pin be called A. So this will be AY and this will be AX. Needn't be in this direction, but I'm just taking it to be as of now. So what this says is this force is applied at this instant such that this reaction, 1 minute, such that this reaction is zero. There is no horizontal force. So yeah. So the point of application of this would be, this special point is called the center of percussion of the body. So basically it does not generate any force at that point. Essentially what will be happening is, because of this force, the one component of this force will have to be balanced like that, and then because of the virtue of this distance, the force of application, it will have some omega, so rotation like that. Now this rotation would have to be countered by two forces like that. So basically both those components nullify each other. So this special point is called the center of percussion of the body, where it does not generate any horizontal force. So I hope that is, yeah. Yeah, so essentially there will be no reaction here. Yeah, see, okay, let me take it like this. I have applied a force like this. So under the action of this force, if this pin was not there, it would have to undergo translation, right? So that translation would have to be arrested by one force. Pin would apply. Pin would apply a force like that to arrest that translation. So far, so good. Now another thing is, this body is also rotating. Actually speaking, it is only rotating. What I'm trying to say is, if this pin was not there, this thing first would have translated like this. I'm just decomposing the motion into its components. So this translation first has to be arrested, which will be done by an AX that will be applied in this direction. Secondly, this will also rotate. This will have a rotation like that. So that rotation, if I allow that rotation, let us say if this is the initial configuration, next at the next instant the configuration would have to be this, right? Because of that rotation, if it were allowed. But this movement is not allowed. So the pin would apply a reaction like that in order to counter that rotation. Both these quantities, the reaction applied to counter the rotation and the reaction applied to arrest the translation, these two equate with each other and nullify when you apply the force at a point, special point called the center of percussion of the body, which has to do with its mass distribution. Is it clear? Yes. P, this point P is the center of percussion for this body. Yeah, A exactly. So AX wouldn't exist now. When I apply this at P, see, that is what I'm saying. The motion of this object can be decomposed into two under the action of this force. But since it is having only rotation about this, ideally, if this was freely rotating, it would have gone like that, let us say. So this is not allowed. So there would be a reaction mobilized like that. Secondly, if this was simply translating, it would have gone here. But that is not allowed. So there will be a reaction mobilized like this. These two reactions will nullify each other when you apply the force at this special point called the center of percussion, which is a function of the distribution of mass. No, if there is no force, why would there be a reaction at all? Frame analysis meaning you mean truss analysis. Yeah, yes. When there is rotation allowed, when it is actually moving. See, this is having some mass. Now I have applied, so this will have some. If this has some mass, it will rotate. About this point, it will go like that, right? But depending on what force I applied, there will be some reaction mobilized here. If I did not consider this point to be the center of percussion, if I had just applied it somewhere, there would be some reaction mobilized at that point because it has to arrest whatever degree of freedom that is coming about that is getting mobilized at this point, that would have to be nullified by the reaction forces. It just so happens that at this special point when we apply, this reaction nullifies and goes to zero. If I were to apply the force even at some other point, slightly this way or that way, there will be some reaction mobilized whose direction you will have to gauge based on the configuration and the moment of inertia. Yeah, yeah, just a moment. So it was something like that. This is the question I think you mean. So let us say there was a particle here. It's a circular. Yeah, what are you asking now? This was? Yeah, yeah, this was the figure. So let us say this is having omega, alpha, whatever. Now, may I, could I just ask you just what your exact question is so that I can clarify that? Yes, yes. Yeah, yeah, with the right hand rule, you can gauge it. Let us say that let this direction be into the plane of the paper. Okay, so omega is actually pointing like that, and I is pointing like that. So let me draw it like this. Okay, let this be into the plane of the paper. I hope you can bear with that. So if this is into the plane of the paper, this is minus z or minus k cap. And then I just take this, I bring it here. This is I. So can you see that k cross I will actually lead to a result that will be pointing like this with the right hand rule. Point your fingers in this direction. Point your fingers in this direction and rotate. Your thumb will be pointing downwards, right? The first vector. Oh, okay. That is the question. Huh? So uh, if uh, if let us say the moment vector is r cross f, so our fingers will be pointing here and rotate the fingers towards f. The plane will be our palm. Okay. F will be perpendicular to that palm. No, okay. No, no, no. See, for taking this cross product, now let us say, let me draw it this way. Okay. Let us say this is X. Let us say this is Y. And let us call this Z. Okay. Now let us understand from X cross Y equal to Z itself. So for taking X cross Y, your palm has to be in which plane? Your palm has to be in XZ plane with the fingers pointing towards X. Okay. Your right hand palm has its palm in this plane. The fingers are pointing in the X direction. Then you rotate the fingers towards Y because you are doing X cross Y. In such a case, your thumb will be pointing towards Z. Palm, if it is in YX plane, then okay, let us say palm is in this plane. Okay. Your fingers are pointing towards X. Can you bend your fingers towards Y? Can you rotate your fingers? Your fingers will actually can't rotate in this plane, right? It can only go out of plane. You understood? So always whenever you are in confusion, you just draw this coordinate system x cross y, x, y, z. Then you know that for the right-handed coordinate system, x cross y has to go to z. Similarly, z cross x will have to go to y. And there will be one more combination. Y cross z will have to be along positive x. So that will avoid the confusion. Yeah. Okay. Yeah. It is one in the same. See, you are pointing to two vectors based on one. Instead of pointing those two fingers, that is actually index finger and the middle finger would have to be pointed along those two directions. Okay, let us say with your hand, right now you put your index finger in K and then you put your middle finger in I's direction. You will naturally see that the thumb will point downwards. So, right, right, yeah. So it can either be remembered using those fingers or because cross product is some uh, it is some semblance of rotation is there. So in that case, you can rotate your fingers and see. You try these things out, and if you still have a doubt, maybe towards the end of the course, after week 12, I will see explore the possibility of conducting one comprehensive doubt session of sorts, where all the remnant doubts can be discussed. So if you have any questions regarding that, you can bring that up even then. Okay. Yeah, yeah. All right. Okay, so let us look at this question. A planar rigid body is undergoing curvilinear motion due to the force system as shown. Which of the following represents the correct kinetic diagram for this body is what is asked. So now we know that given a body, if it is undergoing a rectilinear translation, let us say this is the center. Let me not draw a circle, let me draw an ellipse maybe. Let this be the center of mass because of some non-uniform distribution. This is the center of mass. If this is undergoing rectilinear translation, let us say that I have applied a force like this. Now this is the free body diagram for this. Considering its mass also, let us say its mass is like that. Now if I know that this will undergo rectilinear translation, what will its kinetic diagram be? Its kinetic diagram will basically have one component of acceleration along some generic path. So this will be acceleration of g times mass. So these two, we equate these two in order to find our unknowns, whichever those are. Similarly, if this body were also rotating, let us say, so this will have some moment. Let us say by some distribution, this is also rotating. So about this g, sorry, this we call this g instead. This won't be g. Okay, so in addition to this, it will also be having an angular acceleration. So in addition to its linear acceleration, it will also have an angular acceleration, which will be governed by its distribution of mass. So it will be ig alpha. So this is the most generic case of general plane motion where it will be having mag vector and ig alpha vector. If rotation doesn't exist, if it is pure translation, then naturally there will be no alpha component. There will be only vectors along g vector. That is, there will be only rectilinear translation. And these we know we can resolve these into x and y components or y and z components depending on our convenience. Similarly, if it were undergoing, that is the case for rectilinear translation. If let us say it is undergoing curvilinear translation, the rotation still doesn't exist. Only thing is this will instead of x and y, it will have some intrinsic coordinates that are intrinsic to that curve, especially. For example, if it is a circle, it will be radial and tangential direction. If it is an ellipse or some other curve, it will be one component will be normal to that path, one component will be tangential to that path. So those will be the two components of AG in that case. For a general plane motion, we will have both the vectors. Now let us say it is undergoing only fixed axis rotation. In such a case, AG and I will get linked by the point of rotation. If this is rotating about this point, AG and alpha will get linked by virtue of this being in rotation. So naturally that is where our circular motion equations will start coming in. So with that background, if we were to see, the question already says that this is undergoing curvilinear motion. In such a case, first thing we have to understand is that it cannot have a rotational analog. So Ig alpha cannot exist. So there is only one option where Ig alpha doesn't exist. And since we have been told that it's a curvilinear translation, this is getting emphasized by the fact that we have a normal and tangential direction. If it was a linear this thing, then there will be no normal, only tangential, because this is a curve, whereas this is straight. So in case it is moving along a straight path, there is no need for a centripetal acceleration, in which case only tangential acceleration will exist. So that is why this is the correct answer. So yeah, yes, it will be general plane motion along a curve. So it is going already translating along a curve. Its center of mass is translating along a curve, and it is also rotating about its center of mass. No, no, no. What I meant is, let us say the body is like this. This is not a good example. Let me take the duster example that professor has discussed in the lecture. So if I were to take this, wait a minute, some issue with the, okay, let me take this to be the duster. One is its path is like that, and then this duster, this thing moves like that. So that is curvilinear translation. In the second case, it moves, rotates. It is doing both simultaneously. So you said that general plane motion and curvilinear translation are different. Yes, but general plane motions, one component is translation, right? That could be curvilinear is what I said. And along with that curvilinear motion, it can also have a rotation about its own g. its own center of mass, in which case it will be general plane motion. Is it clear? Ah, general plane motion. Yes, yes. No, no, no. When we are saying general plane, we are already consuming one translation inside it, right? That translation happens to be along a curvilinear curve. It's a curvilinear translation. Okay. Yeah. Okay. So this is done. So yeah, this was the question. Okay. So let us take a look at this problem which got missed out in the live session. So I'll just cover this now. So it says a uniform slender rod of length 1.5 meters and kg, that is the radius of gyration about its center, mass center G, is given to be 0.43, is hinged at one end and suspended as shown. The distance Rp in meters from the hinge such that the application of the force Fp at this point P results in zero horizontal reaction is what is asked. So this distance Rp is as such that when the force Fp is applied at P, it leads to no reaction at the supports. So as we discussed, this is nothing but the center of percussion of the body, the distance to the center of percussion. So let us try to see how to go about solving this. Now let us say that I replace this pin with two reactions. Let us say that I replace this pin with two reactions. Call it point O. So this will be OY. And let us, for the sake of argument initially, let us say that this OX does exist. The question asks at what distance will this OX cease to exist? Okay. So this we have drawn the free body diagram with one point missing where the mass has to be drawn. So we have mg pointing downward. We have the force. Now if I were to draw the kinetic diagram for this, I know that it will be undergoing fixed axis rotation about the point O. So let us say that it has some rotation ig alpha, and then its mass center will have a acceleration. Let us say this is ig alpha, and then the mass point has this acceleration mag x. Let us define this as x, this as y. Now although my force is clearly pointing towards the left, the rotation would be opposite, but as we have done an umpteen number of times, I am assuming that to be positive. And then the answers we will get will show that it is indeed negative. Okay, and then anything else, I also have to account for the centripetal acceleration of this point. So that will be MAGY. So we have completed the free body diagram and the kinetic diagram. So let us apply the equations of motion. Essentially, if I were to add up forces along x, that will lead to MAGX. So this gives me what? OX minus. So I'm adding these up, OX and then minus FP. These are the only two forces in the x direction. So OX minus FP gives me MAGX. Now I know from virtue of this being in fixed axis rotation, I know what AG is. I know how AG relates to alpha. Alpha into this distance is AG, and that distance is nothing but L by 2, 1.5 by 2. So let us substitute that. So this gives me OX minus FP equaling M alpha L by 2, where L is the length of the bar. So far so good. So we have got one equation here. So this is equation number 1. Alright. So this is point O. Now if I were to add up the forces in the y direction, OY would show up, MG would show up, and then AGY would show up. But our focus is on calculating a constraint where OX equals 0. So naturally adding up forces in the y direction is not going to contribute anything, although it might give what this reaction is. We are not concerned about that for the time being. So I will just focus on taking the moment. So let us take the moment about O. Writing the moment equation, let me take this moment about point O. On the right side, since I am not taking moment, if I were to take moment about G, I will have only Ig alpha coming into the picture. Since I am taking moment about O, so this Ig alpha plus the contribution of these two forces will also we have to account for, these two kinetic quantities. This is passing through O, so this will not have any contribution. This will have a counterclockwise contribution with the lever arm being L by 2. So let us write that out. So this will be nothing but Ig alpha plus M A G X into L by 2. Very well. So let me substitute what the left hand side is. Left hand side, if I take moment, I know that this is the lever arm. So FP will create a clockwise couple there, and then there is no other force applied. Mg passes through that point. So I have on the left side, I have minus Fp into Rp, since this is clockwise, equaling Ig alpha plus MAG x into L by 2. So I have this equation now. This is the second equation. So let me simplify this a little bit. So this is FP equaling Ig can be written as mkg squared. We know that mkg squared alpha plus, can I substitute alpha agx in terms of alpha? So that is nothing but alpha L by 2 into this L by 2 that is already there. So this is all I have done. So let me simplify this further. So this gives me Fp Rp equals m kg squared alpha plus m L by 2 squared alpha. Okay. So this follows that minus Fp Rp is nothing but m alpha into kg squared plus L by 2 the whole squared. So from here I can see that Rp is nothing but m alpha by Fp, m alpha by Fp minus kg squared plus L by 2 the whole square. So we have got one expression for alpha. What are the unknowns here for the time being? We have to eliminate these quantities so that we can get the value. So let us use this equation for that. If I were to see this equation and then substitute it here, what will I get? From here, from this equation, I can see that Fp is nothing but Ox minus m alpha L by 2. So this is, let us say this is equation A, which is nothing but 1 in one different form. So if I were to substitute this into my above equation, what will I get? So this gives me Rp is equal to minus m alpha divided by Fp. Fp is Ox minus m alpha L by 2 into this quantity. It will naturally come to this quantity. So this is my actual variation of Rp, actual distance Rp. Now what, applying the constraint condition. Now applying the constraint. This, mind you, this represents the generic equation for this distance rp. That is, if a force is applied at any rp, this is how this has to hold for this system. Now the constraint says that Ox is actually 0. Ox is 0. So I have to equate this to 0. So let me take this. For the center of percussion, Ox would have to be 0. So if I were to apply this to be 0, I just remove this. So the minuses cancel out. M alpha cancels out. So what do I get? I get this quantity in the numerator divided by L by 2. So this is what my distance comes out to be. So if I were to write it a little neatly, what this says is kg squared plus L by 2 squared by L by 2. So this is my distance of the center of percussion from the pin O. Now in the lecture it is given, it is k naught squared by r bar. If we can see, this is nothing but how we will get k naught squared? It is kg plus L by 2 whole squared. So it is the same. R bar is the distance of the center of mass from the hinge point, which is nothing but L by 2 in our case. So these two are same. So we have done nothing but derived this equation from first principles in order to see how this is done, in order to get a feel of the problem. So let us substitute. What is kg given in the question? It is 0.43. So this is nothing but 0.43 squared plus L by 2. L is 1.5 by 2 squared divided by 1.5. So from here it follows that Rp for this configuration is 0.43 square plus 0.75 square divided by L by 2 divided by 0.75. So this comes to 0.996, which is nothing but equivalent to 1 meter. So this is the distance of the center of percussion from that pin O, provided the mass is distributed in such a way that kg is 0.43. Nothing but 0.43. So this distance is equal to 1 meter. This question implies that at 1 meter distance, when I apply Fp, provided the mass is distributed for this rod in such a way that kg is 0.43, this reaction will go to 0. So I hope that that is clear. Okay, so let us take a look at this. So it says a uniform plate of mass 2 kg is connected to identical massless links. So we have a plate and then it is connected to two massless links being the keyword. So a moment of 15 Newton meter is applied to the link AB. So to this link, a moment is applied at A, and the link has an angular velocity of 3 radians per second at the instant shown. Okay. So answer the following questions based on the given data. The type of motion undergone by the plane is what? Is what is asked. Now we have seen umpteen number of times that once we can decide the velocities of any 2 points on a rigid body, then we can find out its motion totally. In such a case, if we see this rigid body, its velocity will have to be perpendicular to that. If I take the link AB itself, in link AB, my B will be having a velocity like that. Since that is connected, VB will have to be perpendicular to this. Similarly, at point D, it will have to be perpendicular to this. In such a case, if I take my plate, I can see that I have two velocities which are parallel and equal. In such a case, I can see that this will also be having the same velocity, and this is having curvilinear motion. At the next instant, when the links will be like that, the velocities will be pointing like that. So essentially, I have a plate which is having a velocity which is tangential to a curve, basically a circular curve. So this is undergoing circular curvilinear translation along a circular path. Is it clear? Okay. So by virtue of that, we can answer that the type of motion of this plate is curvilinear translation. Now, why are there questions time and again asking us to identify the type of motion is what we should ask. The idea is once we know the type of motion, we can quickly identify that once it is curvilinear, it will not be having any rotation. So there is no Ig alpha component in its kinetic diagram. Similarly, when I know that it is undergoing curvilinear translation, I know the acceleration directions. One will be normal to that path, one will be tangential to that path. So it basically simplifies my solving. Okay, with that, yeah, at any other point it can rotate. No, if we remove any link, then we are not talking about this configuration at all. But if we are analyzing this configuration, at any point it will be undergoing translation, curvilinear translation only. Because we have, by virtue of these pins, it will have to undergo curvilinear translation only. Yeah. Yeah. Yes. Naturally. Yeah. So if the lengths were different, let us say that this arm was connected like that. In such a case, its velocity, two velocities are not parallel. We can clearly see. In which case, it'll be having rotation also. So by virtue of this being equal, this the path undergone by this would be a circle. Let us say that this is the circle, be a circle like that. Similarly, this will also undergo a circular path like that. In which case, the entire system is undergoing a circular motion. Okay, so at this instant, what have we been given? That omega AB is nothing but it is, where is it? 3. So it is clockwise, so it is minus 3 k cap. We have been given this. So the point B, we can see, I'll erase these so that the points become clear where the points are. Okay, so let us start by drawing the free body diagrams. So let me go to a page. Let this be my plate. Now I know that this has some weight mg. So I have been given that this is 2 kg. So this is, I have my weight, that is 2 kg, 2g. And then I have the pin's reaction. So there will be some reaction by the pin. Call it by. Let me call this bx. Similarly, there would be two reactions over here. What is that point? D. So call this dy and call this dx. Okay. So its free body diagram is complete. Similarly, I have to draw its kinetic diagram. Now I know this is the path. So let me resolve it along that path. See, if this is 30 degrees, then if this is 90, then this is also 30. It is clear that that is also 30. In which case, this angle is 30 degree. So this will be having M A G. AG, let me call this tangential. Okay. Similarly, there will be one perpendicular to this. So this will be MAN, MAG normal. Now, in a general case, I will be marking alpha also, IG alpha also. But since I know that it is undergoing curvilinear translation, there is no rotational analog in this case. Very well. So this I have drawn for this plate. Now let us come to the links. Now I have my first link like this, which is AB. So for link AB, I know that pin would offer a reaction at A in the x direction, link AB. And then I would have a reaction in the y direction. Similarly, since I have already specified what the directions are over here of Bx and By, once this is specified by Newton's third law, this also becomes known. The direction gets fixed. So this will be By. Similarly, this will be Bx. And then I have moment of 15 Newton meter. So this is my any other force, any other moments are there. I have two reactions at the pins each. Basically, one reaction resolved into two components at the pins each, and then I have a moment. So this completes the free body diagram for this. Similarly, if I were to draw the free body diagram for my, okay, let me draw the kinetic diagram also for this. So now comes the key. Now we know that this will actually be having some rotation, right? And then similarly, by virtue of this, mass of this mass of AB, AG, tangential, and then I have one component like this, mass of AB, AG, normal. Only thing is this will get tied to this alpha because of the rotation. So far so good. Now one thing we must note is this question has specified that this is massless. In which case, what is Ig alpha? Ig is basically mass kg squared. So when this is massless, basically all these rotational components are making negligible difference to the outcome. In which case, even if I were to apply, let us say, moment about A will be what? From the kinetic diagram, what will it be? First, I need to add Ig alpha. About this point, when I'm taking the moment, this naturally gets transferred. This component is passing through that very point. So uh, this has no component there. This will have a component like that. So I have actually marked it in the negative direction. So this will be minus Ig alpha minus MAB AGT into LAB by 2. Is it clear? This portion, what I have written? Yeah. Yes. The link is rotating, right? At currently it is like this. At the next instant it will be like this. Next instant it will be like that. So it is having some omega and alpha, right? Which body? Yeah, exactly. See, this is a combination of different rigid bodies. As we have discussed, that one rigid body can have only one omega, one alpha. But we are presently talking about an assembly of three rigid bodies. So don't confuse the alpha of the non-existence of alpha with this link. Both are two different things. By virtue of this link, the plate is undergoing curvilinear translation. So we have written this equation. What we have done is balance the moment about A and then its kinetic components come into play. Now let me write this again. What is sigma m about A? It will be minus 15. I am expanding this component based on these forces. So what will that be? Minus 15. Is this angle given? This angle is given as 30 degrees. And then is the length of the link given? Length of the link is not given. So let me take that to be L, and call this is 30 degrees, right? So if I write moment about A, I know this is a couple which is 15, so this is minus 15, and then I have plus bx into L sine 30 minus by into L cos 30 equals this quantity. Let me expand that also. It will be minus MAB kg squared alpha minus MAB AGT LAB by 2. Now since we have been given that the mass, the link is actually massless, these components go to 0. In which case I can see that minus 15 plus bx L sine 30 minus by L cos 30 is equal to 0. So what does this give us? This gives us one equation, px L by 2 minus by L root 3 by 2 is equal to 15 Newton meter. Are we sure L is not? Oh, L is given actually. Okay, L is given, so I'll just substitute that. So this will be dx 3 by 2 bx minus 3 root 3 by 2 by equals 15. So we have one equation here. Very well. Now let us analyze the free body diagram for the third link, which we have not touched till now. The third link is link CD. This is C, this is D, I think. Similarly, at C, I am at liberty to put my reaction directions. Let me call this CY. Let me call this CX. And at D, since I have already specified this, it would necessarily have to be the opposite of this in order to have consistent results. So dy is pointing down, dx is pointing to the left. Dy is pointing down, dx is pointing to the left. There is no other force applied on this link. So I have drawn its free body diagram. Similarly, I'll draw the kinetic diagram. So kinetic diagram is again Ig alpha MCD AG tangential and like that MCD AG normal. Now again, I won't repeat it. By virtue of this being massless, we don't have any contribution on the right side. In which case, I can see that there can be only one force existing here. By virtue of this, if I take the if I resolve these two forces into a generic force, let us say like that. I'm just quoting an example as to why this is a two force member. Let us say that this is point C, and let us say this was the actual force. So this is the reaction at D, and let this be some theta. Now this is C. So sigma moment about C would have to be 0 because the thing is massless. In which case I can see that is R D sine theta into L would have to be 0. Now I know that my magnitude of the force is not 0. The reaction, it is not 0 at D. Similarly, L is not 0. So necessarily this would have to go to 0, which implies that the force can at best be only along its axis. So that is why this is a two force member. In which case I know that I have forces like that. So this is RD. So this is the reaction at D, which can be uh, we know this angle, so we can definitely resolve that into components. What I meant is, when we have components, if we compose them into one force, we can show that it can act, at best be only along its axis. So there is essentially only one unknown here, that is the magnitude of RD. Because once the magnitude of RD either that way or that way is known, I know these two components. These are mutually dependent because of this angle being 30. Okay. So in which case I can replace this. I'll take a copy of this and then put it here. Okay. So now let me just replace it with that force. Was like that. This is RD. I should ensure that I do it in the opposite direction here. Okay. So now that this is done, all I need to do is apply the equations of motion. So I have the kinetic diagram, I have the free body diagram. So I know that sigma F along this n is this direction. And this is T cap. Okay, so summation of forces along n is nothing but MAG along n. Similarly, summation of forces along the tangential is nothing but MAG along T. Summation of forces about, call this G. Summation of forces about G is IG alpha, but this is having 0 alpha because this is not having any rotation. So essentially summation of moment about G will give me 0. So let me apply that, in which case I know that I will get minus. Please note this is my positive n. So this is minus RD. So this is minus RD. And then I have my force. This will have a component in this direction. What will that be? So this is 30. So this is cos 30. So minus bx cos 30 minus by sin 30. And then I have plus, this also would have to be resolved into two components, in which case one component will be in the positive direction. So what will that be? It will be, so this is 30. So it is sin 30. So it is 2g sin 30 plus 2g sin 30 equals m. M of the plate is 2, 2a g t. Now we know, since this is undergoing curvilinear translation along a circle, what will this component be? Acceleration component. It is nothing but centripetal acceleration, which is m omega squared r. So what is omega? Omega is given in the question to be 3. In which case I'll replace this with, this is m omega squared r of that curve. That curve is a circle. So this is 2 3 squared into, what is the radius of that circle? That is the length of the link, which is 3 meters. So I have one equation like this, which gives me what? Minus rd minus bx root 3 by 2 minus by by 2 is equal to 2 3 squared into 3 minus 2 g by 2. This is just g. So I have another equation like that. So I have used this up. Now let us use this one up. So what does that give us? Sigma ft. Now we can see that along t direction this will not have any component because it is parallel to n cap. So in such a case I'll have the other equation. I hope I'm doing it legibly. If there are any questions midway as to how I'm writing this, you please do ask. I take it that it is clear. So since the force is like that, it will have a positive component along t, which will be 2g cos 30. So one is 2g cos 30, 2g cos 30. So I have accounted for this force. This force doesn't come into play. For bx and by, I can write bx will also have a positive component, which will be sin 30. Yeah, this will be sin 30. So bx sin 30. And then this will be having an opposite component. So 1 minute, it will be like that. So this will be cos 30. Yeah. So it will be by cos 30 equals ma gt. Okay. All right. So I have another equation here. Or let me simplify this. So this gives me bx by 2 minus by root 3 by 2 equals 2ag tangential minus 2g g root 3. Now first let us see how many unknowns are there actually. What are all the unknowns here? We don't know what AGT is yet. By virtue of omega, we know what AGN is. It is omega squared r, so that is known. So there is one unknown here. And then there are two unknowns here. 1, 2, 3, and then the magnitude of this force R. So we have four unknowns, so we need four equations. One equation we have got based on the equilibrium of our link. So we have one equation, and then we have 2, 3. Next we have fourth equation. Let us balance the moments. We have used these two up. We have to use this. So sigma mg equaling 0. Okay, so how this will come about? This force will cause a moment like that. Dy will cause a moment whose lever arm will be this. Dx will cause a moment whose lever arm will be this. And then this can also, I can resolve this into two components, which I had done initially. So this will also have component like that. Okay. So let us write that. So sigma moment about G equaling 0 will give us dy into, okay, what are the dimensions of the plate? Is it given in the question? It is 4 and 2. It is 2 and this is 4. Okay, so in such a case, this if this is G, I know this distance is 1. Similarly, this distance is 2 meters. So if this is 1 in this triangle, if this is 2, this is 1, then I can see that this is nothing but 2 square, it is root 5. So why I am doing this is I have a force like this. The perpendicular distance of that force from the CG is root 5. So I need not resolve it into components. I can directly take that lever arm to be root 5. And it is creating a clockwise couple which is negative. So it will be minus RD root 5. And then it will be minus dy into 1. It will be plus dx into 2 equaling 0. So what will this give us? It gives us bx 2bx minus by minus rd root 5 equals 0. So I have the fourth equation here. Bx, by, rd, the unknowns being bx, by, rd, ag, rd, bx, by, and then here I have bx, by. So I have all the four equations having only these unknowns. So I can just cast it as a matrix. I'll just write the matrix now. You can take the inverse in your own time. When I'll post this sheet, I will, I'll post it after solving this question. So I hope that that is okay. Yeah. If we remove a link, in the what does in the direction of that link mean? Along the axis of that link. Okay, but that is provided the link is not acted upon by any other force. If it is a two force member, then yes. In this very question, we saw that we have a link which is not acted upon by a force. So at best, it can only support a axial force. So when we remove this from the plate, we naturally put that. force like that. We have, right? I have only magnitude. Ah, okay. No, but this is actually having a force, right? This this link. Where is that link? This link is having a couple applied, right? The reactions would have to mobilize. The reactions would have to mobilize such that this is also balanced. We saw when we took the free body diagram of link CD, I can see that there is no any other force that is applied here, right? So I just resolved this along a generic direction. Let us say this was the force, this was the reaction at that pin. I have resolved it along some generic direction, RD, theta, and then in the absence of any other force, I add up the moments and find out that theta can at best be 0 in the absence of anything else. If I have a force here, if I have some moment here, then my theta will have to be theta and RD. RD sine theta, what I mean to say is this magnitude and this orientation would have to adjust to that moment. It is only in the absence of that that it is a two force member. Yeah, in the absence of any other force, it is only a link that is having two end forces. In a link which is having only two end forces, we cannot have such a force system. At best, we can only have a axial force system. Yeah. Okay. Okay. By virtue of these two being equal and parallel, we know that this cannot support moment. If this is indeed applied with a moment, then this reactions would have to be mobilized accordingly. Yeah, that's what I'm saying. You are applying a moment to this plate. In this case, it cannot have a rotation about its own axis by virtue of this connection, in which case there will be reactions appropriately mobilized to counter that moment. We are doing this, right? Sigma m equaling 0. See, in this free body diagram, you are saying there is one additional moment. That is all you are saying. In addition to this weight and these reactions that are coming by the pin, if there is one additional moment, right hand side still remains same. It cannot rotate. It can at best undergo only curvilinear translation. So where will that effect of that moment go? That will get adjusted into these quantities. The magnitudes will mobilize themselves to counter that. By enforcing that equilibrium only, we are finding these, right? Yeah. Okay, this is one. This is the second equation. This is the third equation, and this is the fourth one. So if I have to write this in as a matrix, bx, by, rt, and ag, let us say agt. So from the first it is 3 by 2, by is minus 3 root 3 by 2, 0, 0, this is 15. Second equation gives me bx is minus root 3 by 2, minus 1 by 2, rd is minus 1, 0, and this gives me this quantity. 1 by 2 minus root 3 by 2, 0 minus 2 minus 0 3. This is 2 minus 1 minus root 5, 0, 0. So we can just invert this matrix and get the unknowns. You can also systematically solve these equations and get it. Either way, whichever is comfortable for you, you can do. Okay, so I take it that this question is clear. There are only some subtle aspects that we need to identify. Rest is only just algebra, adding up the numbers, which is a little boring. What are the key takeaways from this question is, by virtue of these links being equal, first we identify that this plate is undergoing curvilinear translation with that curve being a circle. This is having a circular path, this is also having a circular path. When two paths are same in a rigid body, then naturally all the paths would have to be same, congruent. So this is also undergoing a circular curvilinear translation along a circular path, that is insight number 1. Secondly, we saw that if there is a link in the absence of any other force, if the link has only forces at the ends, then that can at best be only along its line of action. By virtue of this being massless, we saw that no matter how we add up the moments, it is not, its angular acceleration and omega are not coming into play because m takes it to 0. So what does this tell us? This tells us one important aspect, that let us say if I have a string and I tie a stone to it and then I'm rotating it, the strings components are not actually playing a part in this, in which case I at best I can take that mass at the end of that string and do my calculations and I won't be way off. So by considering this mass of the string or mass of the link, what effect that brings into the question, you can basically assume what the mass is, and then maybe if you come across a question where a mass is given and then in the absence of that mass, the relative magnitudes, how different they are. That is why we say that this is massless as compared to this plate. So that is insight number 2. Rest is all vector algebra, so that you are familiar with. So in that case, I will, whenever I post this sheet, I will solve this threadbare, these equations, and post it along with the answer. Provided I'll also ensure that there are no calculations error, because I'm also solving it live. There is a possibility of some addition, subtraction here and there. Mainly, we need to grasp the concept strongly. Okay. Okay, let us look at this question. So a motorcycle rider, a motorcycle riding on a pavement as shown in the figure, has a mass of 150 kg with its center of mass at G1. Where is G1? This is G1. This is the mass of the bike. The rider has a mass of 80 kg and has his center of mass at G2. At this instant, the rider decides to perform a stunt, that wheelie, where basically it just lifts off from here, where he lifts the front wheel onto the pavement and rides only by the back wheel. Considering this situation and neglecting the mass of the wheels, why we are neglecting the mass of the wheels, the ig alpha of that is not coming into play. That is the implication of this. Whenever we see it is massless, you need not consider its rotational analog and its mass into kinetic components. That is what this implies. So answer the following. So the normal reaction at the back wheel, the maximum acceleration necessary to do this stunt, and the minimum coefficient of static friction required between the wheel and the pavement in order to perform this stunt is what is asked. Okay, so let us go about drawing the free body diagram again. Now at this instant when it has left the contact here, it is undergoing rectilinear translation. Just that this has lost contact now. So the entire thing has to be mobilized by two components. One is the normal component and one that is the friction acting at this point, which would have to balance mass and whatever the kinetic quantities are. Kinetic quantities, it is undergoing only rectilinear translation with two masses separated. So essentially this will be undergoing m g1 mass of bar into a bar, and this will be m g2 mass of bar into a bar. Body system is undergoing one acceleration, which is what is asked, what should be that acceleration, and this will get distributed into two kinetic quantities. So in this case, let us draw the free body diagram. So okay, let me try to draw it in some sense so that it matches. Okay, I take it that you can figure that out. I don't want to go into this. So okay, what is the mass of the bike? That is given to be 150 kg. So I have 150 g here. Then this is the mass of the person riding the bike. This is given to be how much? 80. So this is 80 g. At this point, there would have been some normal reaction, but since the condition, the constraint given in the question stipulates that there has to be loss of contact there, I will not draw the reaction force there. So there will be a reaction force here at C. And then we will have a friction at this point, which is Fc. Any other forces we have not accounted for. We have the mass and we have accounted for the externally applied forces onto the system by the road, by the pavement, whatever. So this is the free body diagram and this is the kinetic diagram. In the kinetic diagram, these components will not come. Basically, this system is undergoing rectilinear translation. So this is m bike into a g x, and we have another kinetic component m person or rider, what shall I say, into ag x. It should be noted that these two are same. As a system, it is same. The person is not having any relative acceleration relative to the bike. Otherwise, he would fall off. So, the question implicitly assumes that there is no, there is no relative acceleration between the two. This entire thing is treated as one system with separate g's, center of masses. So we can also take moment about some point and calculate the effective centroid of this entire mass, effective center of mass of this object, in which case our kinetic diagram will only have one point, which will be having m effective into agx. But since it has been broken down into two components, there is no harm, we can also do that. Okay, so now, yeah, yes. Why? Okay. In this case, this is this point. If the in the absence of friction, it would have gone like that, right? No, this is friction applied on the system by the pavement. That would have to propel the system forward, no? Okay, let us say that I don't take this. What do you anticipate it would happen? What do you anticipate will happen? Based on what? It will just keep rotating, no? No, no. What I'm trying to say is the pavement is applying a friction in this direction to propel it forward, propel the thing forward. Yes, impending motion of this point is in which direction? It is this way. Why it is right? No, no, that's fine. This wheel as a whole, it is rotating, right? You are talking about a box where you're talking about a box where it's if its impending motion is this way, I will apply friction in the opposite direction. Fine. We are talking that motion is being achieved by the rotation of this wheel. At this instant, if there was no friction, the tendency of this point is to go that way, which is opposed by the friction from the road, which is what propels the vehicle forward. Okay, yeah. No, no, don't be sorry. It's a good question. You think it over. If you are not convinced, you feel free to get back at any time. Okay, some things can be counterintuitive. There is absolutely no issue in asking all that. So even after upon reflecting and ruminating on this, if you find that you are not convinced, you are always free to get back to us. Yeah. Okay. All right. So we have, yeah. Anyway, the non-zero accelerations are only these. So I take it that the person is not going through the floor, in which case there will be no acceleration in this direction, that is zero. Okay, so let us apply the kinetic equations. So what do we know? Sigma fx equals mg m. Uh, Let me use this convention. It is getting rather. I'll use it as mv and then m rider. I'll use it as mr. With this convention in mind, I'll just write these quantities. So this will be mb ag x plus mr ag x. So what all are the forces in this direction? We have F at point C is equal to what is the mass of the bike? It is 150 plus 80 into AgX. So we have one equation over here. Similarly, if I were to add up the verticals, I know that this will be MGA Y with the understanding that the person is not going through the floor. This is 0. So what will this be? RC. I have put one reaction at C that is countering the total weight. So this is 80 plus 150 G. So I have this 80 plus 150 into 9.81. So this is 2256.3 Newton. So RC we have readily got as 2256.3 Newton. Okay. Now what is asked? Now let us take moment about this point. We know that this is not having any alpha. This is not, at this instant, it is only undergoing rectilinear translation with loss of contact at this point. In which case, I have no rotational analogs here. But I can always take moment of this about this point. So let me go ahead and do. I can basically I can take it about any point. My unknowns will also start appearing when I take moment about some other point. So I am just cutting down my work by taking moment about this where I know FC and RC are applied at that very point. It can be solved either way. So let me take moment about the convenient point C is equal to Ig of the system into alpha, where alpha of the system. But this is not all. Since I am not taking about its G, see, this is Ig alpha. Okay. Now, since I am not taking about G, these kinetic components will also have a rotational effect there, in addition to this Ig, which happens to be 0 in this problem. Okay. So what will that be? Minus, I have this will create a moment like that. What will the lever arm of that moment? It is this 0.5. Another will be 0.5 plus 0.2, which is 0.7. So this will be m bike agx into 0.5 minus m rider agx into 0.7. This is 0. So this I have not expanded. From the free body diagram, I have to expand that. When I take moment about these two, naturally FC and RC don't appear. 80G and 150G appear. What will be the moment arm for 80G force? It will be 0.25 because 80G is acting like that. 80G is acting like that. This will be 0.25. For this, it will be 0.25, 0.55. Okay. So this is also in the clockwise direction. So I'll take that also to be uh, negative. Basically, it will be a negative contribution. So this is minus 80G into 0.25 we saw. 0.25 minus 150G into 0.25 plus 0.3, I think it was 0.3. Any other forces left? Yeah, I have balanced everything. So this will be minus, this will be this quantity. This will be equal to this. So the left side is totally known. Right side AGX is what is asked. So I can solve for AGX from here. Let me do that. What is the left side? 9.81 into 0.25. 9.81 into 0.25 plus 0.3. So this is, yeah, yeah, yes, yeah. Now what are you asking? You are talking about a case where this would have lifted like that, in which case weights will still be. Yes, but we are analyzing at the instant where reaction goes to zero. That is, it has just lost contact. What happened? See, after this moment on, when the person is performing a wheelie, the person will also have some angular acceleration. the system will also have some angular acceleration. At this very instant where this r, what is that point? When this rd has actually gone to 0, it is at that instant that we are analyzing this. If you take at some other instant after this, this entire system would have acquired some angular acceleration also by virtue of that person rotating about this point. Yeah, I understood. I understood. You are talking about a system when it is like that, but weights will still be acting like this. Yes, it is no longer 0.3, it will be something less than that. The mass will be somewhere here. So this will be that distance. Is that what you're asking? No, it is not a it uh, one thing is it will have a minuscule effect, but that is not the reason why we are doing this. That is what I'm trying to say. See, we are not considering the motion of this point to this place, is what you are saying. That we are not consider this would have moved here when the person starts to do that stunt, and you are saying that the mass would actually be acting here. We should essentially compensate for this distance, is what we are discussing. What I'm trying to say is it is not that we are ignoring that, considering that to be minuscule. We are indeed analyzing the system when the reaction has just gone to 0. At that point, mass will still be here. It is only at the next instant that it would move, and it is at the instant when we are considering when angular acceleration is 0. After starting this point on, the system will have an angular acceleration which will be non-zero. So just because there is a slight movement and we are ignoring it is not the correct reason for this, is what I'm trying to say. We are not considering it. You might form an opinion why we are not considering it, thinking that it is minuscule. What I'm trying to say is it might be minuscule, but its magnitude is irrelevant here. Why we are not considering is because we are focusing at the instant when it has just lost the contact. Is it clear? Yeah. Both are two different things. Both might lead to the same. For example, if we see nonlinear equations, they will have multiple answers. So there could be two nonlinear equations which will have the same solution, or one which can have multiple solution. We should be correctly identifying the reason for that. Since we have not marked any alpha here, we are considering the instant where this RD, actually why not I write it, RD has just gone to 0. That is when we are considering this. Very well. So this is all right. On the right side it is, what is this? AGX into minus MB is 80 into 0.5 minus 1. Sorry, this is MB is the bike, right? So this is 150 into 0.5 minus 80 into 0.7. So what is AGX come out to be? Minus 1005.525 0.7. So this comes to 7.668 meters per second square. So this is the acceleration the person would have to give at this instant for this loss of contact to actually happen. If the acceleration is anything below that, the loss of contact doesn't happen. Why it doesn't happen? Does it understand that we have assumed loss of contact? It is because we have calculated this value with the pretense that this doesn't exist. So only when this doesn't exist, that acceleration will hold. It goes back and forth. Okay, so this minimum acceleration is 7.68 meters per second squared. All right. So we have got this reaction. We have one more equation over here. If we know this, then we can find out what Fc is, which is nothing but this is 230 into this 7.68. What does that come out to be? Answer into 7.68. So this comes to mg kg. Okay, yeah, sorry, this comes to 1766.4 Newton. So once we know Fc, once we know these two quantities, given that it is impending motion, we just have to take the ratio in order to arrive at the coefficient of friction. Fc we know. Do we know R? We know it from here. So therefore mu is what? Divided by 2256.3 comes to 0.78. So this is the minimum coefficient of static friction required to mobilize such an acceleration such that RB goes to 0, which enables the person to do this stunt. So all these are linked by this storyline. So I hope that that is clear. So if there are any questions, please feel free to ask. Okay, in the meantime, I'll go forward and look at this question. Okay, so the question says a disk of mass 6 kg and radius 0.5. Where is the disk? Is here. So this disk has a mass of 6 kg and a radius 0.5 is connected to a light cable which is wrapped around two frictionless massless pulleys. One pulley is this is one pulley. The block of mass 9 kg, this mass is 9 kg, is suspended vertically from one pulley. So we have this, so it goes like this. So this is suspended from this pulley. It is known that the disc rolls without slipping on the inclined wedge. Okay, so the disc rolls without slipping on the inclined edge. Based on the given data, answer the following questions. So let AM and AG denote the magnitude of accelerations of the suspended block and the disk's center, respectively. The ratio of these two is what? Is what is asked. So let us see it like this. Let me make a copy of this. So let this distance, let me label that as something. Let me label that as A. Let this distance be some B and let this be C. This I'm just ignoring these for the time being. Let these be some constant D. Okay, whatever is uh, lapped around the pulley, I'm not considering that for the time being, but that will be the same no matter what motion happens. So okay, let me consider that also. So from here, the length of the cable, is it called a cable? Yeah. So I'll also write cable. Let this be LC. Okay. Let the length uh, lapped be LL. So let us proceed with this convention of naming. So from here, so from this figure, we can see From this figure, we can see that A plus B plus C plus L labbed all makes up the length of the cable LC. Okay, now I know that this distance doesn't change from here to here. Both these quantities are not moving, so C remains fixed. Similarly, L, the lap length also remains fixed, and the total length of the cable is same. In which case, let me take the time. Yeah, 2B. Yes, sorry, 2B. Good catch. So A plus 2B plus C, thank you for that, plus LL is equal to LC. So taking the time derivative, what will this give me? A dot plus 2B dot plus C dot plus LL dot equaling LC dot, where these quantities are 0. So what does this give us? A dot is minus 2B dot. So from this, if I differentiate this again, A double dot is minus 2B double dot. So what A double dot is the acceleration of the center of mass of this disk. Similarly, B dot, I have taken this. So B double dot represents the acceleration of the mass downward. So in which case, AM, A double dot, AG, sorry, AG is A double dot, and AM is B double dot. So we can see from here that AG is nothing but 2AM. Therefore, these are representing the magnitudes of acceleration is what is said. So please note that. So acceleration of G comes on top, M comes on top. So we can see that it is half. Very well. Okay. So now let us go on to see the next question. Determine the moment of inertia of the disk Ig in kilonewton if the radius of gyration is this. Mass of the disk into kg squared is the moment of inertia Ig, which is nothing but, what is the mass of the disk? 6. So it is 6 into, where are we? Which is nothing but 2.13 kg meter squared. Determine the magnitude of acceleration of the disk's center. So far we have only got the relation between these two. We have to work out the acceleration also. Okay, that we'll do. Determine the tension in the cable, determine the magnitude of acceleration of the mass m, and then determine the magnitude of the angular acceleration of the disk, the coefficient. Oh, many things are asked. Okay. So let us go about doing it one after the other. So let me draw the disk here. We've been given the angle. Angle is given. Okay. So it has a tension like that, and then it has a mg m disk g by 2 by virtue of this being sine 30. This is 30 degrees. And then I have a normal force N. I have a this will be m disk g root 3 by 2. And then I have friction, and then the kinetic diagram for this. So I know that this is rolling without slipping. So g is having an acceleration like that, mass of the disk into a, what did we call that? Name that something, right? Ag. Ag, yeah. And then it is also having, so rolling without slipping is a case of general plane motion. So Ig alpha also comes, alpha of the disk. Okay. So now we have the kinetic diagram and the free body diagram. So let us write the equations of motion, in which case let me take the sum of forces, or yeah, let me take the sum of forces along this direction. Let me call this x, let me call this y. So summation of forces along x gives me mass of the disk agx. So what does this come out to be? This is T plus Fr minus M disk G by 2 gives me Gx. So this gives me one equation. Okay. Similarly, taking summation of forces about y equaling M disk A AY AGY. We know that this is not going through the incline. So right hand side is 0. So what this gives us is N is nothing but M disk root 3 by 2. Mg disk root 3 by 2. Mg cos 30, cos theta actually. So at least one quantity we know now. All right. Similarly, if I take moment about some point, let me take it about the center. Moment about G is Ig alpha. Note that if I don't take it about G and if I take it about some other point, then what will happen? I'm taking this about G. So this contribution is 0. If I take this about this point, Ig alpha plus mg into this distance, radius of the disk, will also come into the picture. So let me take the moment about the contact point then. What does this give us? Let me call this point something. What shall we call it? A, B, C is taken. R. Let me call this R. So moment about R. or this will be just minus Ig alpha. So this is what changes when we shift the point where we are taking the moment. Both should give the same result because the results are objective. But this is how it changes, is what I'm trying to emphasize. Here, this is the lever arm. This is not to be considered as the radius of the disk, but this is a lever arm for to the point where we are considering from the point of application of the kinetic quantity. When we consider the center, this naturally goes to 0, which is why only minus Ig alpha would appear. Okay, so let me take that about the center. So this will give me tension minus mg. I'm considering tension to be more because naturally it is moving in that direction. So T minus into the radius of the disk into R disk equals minus what was Ig? We calculated Ig as 0.6 into 0.355. Oh, how is this 6 into 0.355 squared? Yeah, okay. It seems a bit high, that is why I was wondering. 6 into 0.355 squared. So this is 0.75 or 76 kg meter squared. So this is 0.76. This is minus 0.76 alpha, and then minus 6 kg is the mass of the disk, AgX into our disk. Now we know that AgX is tied to this alpha because of our circular motion equations. This is a disk rolling without slipping. So alpha r is nothing but our AgX, in which case I can rewrite this as T minus m disk G by 2 into R disk is equal to minus 0.76 alpha minus 6 alpha R disk squared. So from here this will give one equation which is, okay, why don't I substitute this? It's becoming very messy because of the symbols. R is 0.5, mass of the disk is 6. I'll just substitute for these values. 1 minute. Yeah, so tension minus mass is 6, so this is 3, so this is 3g into radius of the disk. We just saw it was, what was it, 0.5 equals minus 0.76 minus 0.5, 0.25, so 6 by 4. So this gives us one equation. How many unknowns are there? We know tension is an unknown, friction is an unknown, Ag is an unknown, magnitude of Ag is an unknown, and then acceleration of the that mass which is suspended, that is also an unknown. Its acceleration is also unknown. So have we exhausted all the three equations for this? This comes from moment, these two, this comes from force, this also comes from force. So we have done our analysis with respect to the disk. Now let us go to the mass. And how these two get tied together, the disk and the mass get tied together because of this relation, which comes from the constrained motion equation by virtue of this string. So that is how two different quantities get constrained into one system. And then we can solve for the unknowns after that. Okay, so we have got this. Now let us do it for the mass. Where are we? So I have the mass here, m, just m. Let me take that to be m. I don't know what it was named as. So this is connected to a pulley which has cables like that. Now these cables, if the tension here is T, the other tension is also T because we have been given that it is frictionless, smooth and so on. Frictionless, smooth and so on. Otherwise, if we need to add friction also, then we will have to account for friction, how we studied. So the idea is not to involve all the complexities into this question. It is just to emphasize what the main idea towards understanding this is. Even if there were friction, then if this was T2, this is T1, by knowing the friction coefficient, we can relate these two. So that is also, that won't be an additional unknown. Once you know one tension, you can easily calculate the other given the friction coefficient. Okay, so this is the free body diagram of the mass and the pulley system, with the pulley being massless, and the kinetic diagram is would be, this will be having m, a, mass. Yeah, that's all. So that is what it is. So this is having rectilinear motion. It is easy to see that this is just undergoing rectilinear translation, nothing else. So there is only one thing appearing in its relative motion, in its equations of motion. So can we add this up? What will this be? It will give me 2t minus m, should be g is equal to minus m a m of the mass. So I have another equation here. So I have four unknowns. I need four equations. So one equation is this. This is equation number one. This is equation number two. This is known. So this I am not counting as an equation because this doesn't have any unknowns. This is equation number three. And our relation between these two. This is equation number 4. So similarly, as we did for that previous problem where I constructed the matrix and just took the inverse to solve for these, it can be done easily. So I won't go on solving that now. So what I would rather do is when I post this sheet, I will solve this and post so that you can refer to that. In the meantime, if there are any questions, I'm happy to take them because we are almost run out of time. So if there are any questions, you please feel free to ask. Is everything clear? That is questions not limited to this week alone. If there are any questions to be discussed from the discussions of the previous week throughout the course, if there are any, uh, you may ask if you do have. Otherwise, you are always free to ask them in the forum. And towards the end of this course, naturally we are at the 11th week, so there'll be one more week for 3D kinetics. Next Friday we will be meeting. And after that, depending on the need, we'll consider having one comprehensive doubt session of sorts for another 2 hours, maybe the Friday after next. so that we address all the doubts that are coming throughout the course. Yes, sir, Mr. Yeah, please go ahead. Yeah, okay. Okay. It was in the previous section, is it? That is, it was along a circular path like that, huh? Okay. 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 Yeah. Yeah. Okay. I think it was something like that. Okay. Okay. We are finding out the velocity. One velocity will be like this. The other velocity will be like this. Ah. Okay. That's fine. Ah. Okay. Okay. Yeah. I think I understood your question. What you mean is, if I were to fix a non-rotating translating axis to this point and look at this point from there, then I go from vector algebra and do omega cross r and find out the angular velocity of this. What you are asking is, if I know the velocity of this, can I directly find out this velocity by going without going through that vector algebra route? Yeah, as I suppose you were the person who had attended that session, right? Where we resolve this into the axis of the, that is, this velocity is component along the axis of the member, and this velocity is component along the axis of this member will have to be equal by virtue of them being rigid. By that concept also you can solve. Ah, okay. Hmm. Yes, yes. Yeah. I'll just explain that. Let the let the bar be like this. Okay, let its velocity, this point's velocity be like that along the wedge, and this has a velocity like this. Let me color this in green, or rather some other color. So one is, let this be theta 1 and let this be theta 2. VB, VA. Okay, so VA cos theta 1 equal to VB sin theta, sorry, cos theta 2. So far, so good. By exploiting the rigidity of the object, we have been given one quantity, we can calculate the other quantity. Fine. Now, what do we do for, if we don't go by the vector analysis, what do we do for calculating omega? So, if I were to take this is my vector, and the second vector is this. So, this is the actual vector that is coming about. Something needs to be added to this in order to make it go like that. So, if you can find out this vector, let us say B with respect to A. If you can find out this by our normal resultant, you know this angle, you know these two magnitudes. Now that you have applied this, you know these two magnitudes. This angle you know. By applying cosine rule, you can easily calculate this. Once you calculate this, this divided by the length will give you omega of this bar, of this link. Ah, yes, yes. Yeah, that is what I meant. See, these two you know, this angle will be nothing but theta 1 plus theta 2. From with reference to this figure, this will be theta 1 plus theta 2. So VB with respect to A, which is also equal to omega link crossed with RB with respect to A, it will be the square. Let us call this vector C. Okay, so magnitude of C squared is nothing but VB squared plus VA squared minus 2 VB VA cos of theta 1 plus theta 2. And if I take the under root of this and divide it by the length of the link, I will directly get omega. Yes, sine is 90. See, R is like this. R vector is here like this. And omega is omega cross R. So this is 90 degree. No matter what you do, its velocity will appear to be like that. So this angle is naturally 90. So even if you divide it, it will be sine 90. Okay. So I take it that that is clear. Anything else? Any other questions from the previous sessions? Yeah. 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 That is up to you. If you are able to find that out, well and good. It might not be straightforward in all questions. If you can find this point by geometry, nothing like it. Then then this is RA with respect to ICR. You just need to divide VA by RA, and you will get the angular this thing. But that is provided you are able to locate this point easily. If you are able to do that, by all means, you can do that. Yeah, the perpendicular, depending on what your acumen is what I'm trying to say. See, some people don't find this doing sine theta cos theta that hard. They are very comfortable with this. So if like, see, the idea behind teaching the same problem from so many different methods is there is no universal method to apply. Depending on your acumen and your preparedness, you are free to apply anything that you can. Some people might find this locating ICR easier as compared to doing omega cross R. But how this all comes about is from this fundamental equation of omega cross R from the relative analysis. So if what we are covering here is from the first principles and then some shortcuts here and there. So you are free to use whatever comes naturally to you. And if there are any doubts in that, please feel free to raise them in the forum or this sessions as you have been doing so that we can address them. Is it clear? Yeah. Yeah. Yes. Yeah, yeah. Okay. You saw the sheet that I posted? No, no. See, velocities are intuitive. You can gauge that from the problem. Accelerations are not intuitive. You can't, looking at the velocity, you can't say whether acceleration is positive or negative. So applying methods like these works well for velocities. Accelerations, it might not be intuitive always. So it could be slowing down or speeding up. So that I don't think you can gauge that by the figure. But anyway, what is the question anyway you have? So this will have a velocity, this will have an acceleration centripetal like this, which will be along the center of this circle. Then it will have an acceleration like that. So once I know this, I know this is moving in a straight line. So this can only have a linear acceleration. Yeah. So if you are doing this by acceleration polygon, I don't think it is very straightforward. You need to account for very many things. If you have attempted that, I would suggest that you maybe send a PDF of that in the forum, and if there are any some issues with that we can point out. But as such, in this course, the dictum is that we are not promoting calculation of acceleration using these methods. It is better to go from first principles of vector algebra to calculate accelerations because it can be counterintuitive most of the time. Yes, yeah, this quantity will exist. This quantity is there. Yeah. Anyway, what I'm suggesting is you take a relook at the solution. If you have attempted this using acceleration polygon or something, if you have questions, you can post that in the forum. Your solution you can send, and we may be able to point some issues out. But as such, acceleration, we encourage you to go by first principles of vector algebra, unless it is very, very obvious. So I hope that that is clear. Anything else? Any other questions? Okay, so if there are no further questions, because we have also run out of time. So if there are no further questions, I'll stop here, and when I'll post this sheet, I'll ensure that these things are all filled up. In the meantime, if you have any questions, you please feel free to approach the forum and we'll answer. So with that, I'll close. So I'll see you guys in the next session for week 12, which has to do with 3D kinematics. So till then, see you. Thank you. Thank you very much. Thank you.